to Science Talk. I am your host and resident oceanographer Jim Massa.
Well, good evening, everyone, and welcome to Environmental Coffee House. I had a little snafu in the beginning, but I got it fixed in time for us to go live. Hello, Jim. It's so good to see you. It is.
Hi, Paul.
And let
Hi,
me say,
Sandy.
I want to say hi to everybody in the chat really quickly. I want to say thank you, Kim, first of all, for moderating when you're feeling like shit. It's very hard. And hi, Lindsay, Rob. This is great. You made it to Alive and Poppy and But the Truth and Kevin Shandholder. Hi, Vegematic. All right. So listen, if you guys have questions, put two Q's in front of them, and I will try to get them aside for the end of the presentation because tonight Jim has a presentation. Yeah. So Jim, welcome.
Howdy.
Howdy. Howdy.
How's everyone doing tonight?
Oh, looks like they're all joining us and we're getting a crowd. And well, what are we doing tonight, Jim?
Well, I've got some figures that we look at air temperatures, sea surface temperatures, anomalies, and then sea ice, and a couple of
I'm wearing sea ice.
websites
Yeah.
looking at ocean heat, because I'm going to present the argument tonight that a major reason why the planet is warming, a major reason why we're going to see a very strong El Nino, a major reason why we're losing Antarctic ice at a very alarming rate is because of ocean heat content. It's the big elephant in the planet, shall we say?
Yeah.
And there is, when I made my last ocean heat update last January 2022,
Okay.
the estimation was around 250 zetajoules of heat energy absorbed since 1951 or thereabouts. It's over 340, 350, or maybe even up to 400 zetajoules. And when you consider the specific heat content of water, that is, not to put too fine a point on it, a shitload of energy. And since sequestration to depth, i.e. the thermal haline flows are decreasing, the heat is not being sequestered, it's going to linger, and it's going to move around horizontally, it's going to diffuse upwards to the atmosphere, and you get what we're getting. A very strong El Nino, increased melting of ice, warming temperature. Yeah, it's this heat is it doesn't disappear when it goes in the ocean. It doesn't disappear. It's going to be returned.
Oh my gosh. All right. Well, I guess we'll get started with the presentation. Let me get that set up. Of course, I had it set up, and things always go a little kaplooey. All right. All righty. Well, let's get this started, and let me make sure I can see what it looks like. All right. You all can see it looks pretty good to me. Let us get started. Jim, take it away.
Okay, so this is a graph showing 2-meter temperatures, and if you look at it, it goes from 90 degrees south to 90 degrees north, from 0 to 360 degrees east longitude. In other words, the whole bloody planet. So these are, average 2-meter high temperatures. That's the standard procedure, is to measure air temperatures 2 meters above the surface.
All right.
And what you see here is, first of all, let's look at that middle line there. That's basically, when we see what the baseline is again.
Mm-hmm.
But that is basically global average, and the lower dash line is the two standard deviations below the mean, and the upper dash line is two standard deviations above the mean. And when you look at the black line, the orange line is last year, 2022. You can
Mm-hmm.
see how that was basically in a lot of places above the two standard deviations. The
Wow.
black line is 2023 thus far, and we can see, especially in the last recent weeks or so, how the temperature is getting a little much higher
A little warm out
than
there? Mm.
more than two standard deviations, possibly more than three standard deviations above the average. It's warming up rapidly. That's what this is, just air temperature. Granted, air temperature has a lower heat capacity, so it can heat up faster. But this is still an indication, when you look at the last 2 years, that the last 2 years are now basically the temperatures are above two standard deviations. That's not good.
No, I concur. I concur.
Now the next slide is a sea surface temperature. Now, this is just measurements. These are the actual temperatures. You can see the scale at the bottom there. Kind of lean forward a bit, where when we get to the purples and stuff like that, we're talking about 30 degrees Celsius.
Mm.
So, of course, not surprisingly, very nice rainbow colors, of course, but it's the equatorial oceanic regions are extremely warm, and that heat persists even well into the North Pacific, well into the North Atlantic.
Mm.
And we just see extremely warm oceanic temperatures. Around Indonesia is particularly very warm, and we have a very warm pulse right off Baja, along with the other very warm temperatures in that region. This is the indication of the strong El Nino that is beginning. So this is just temperatures. The next slide will show you the deviations of what's going on with temperatures there. So this is again showing sea surface temperatures from 60 degrees south to 60 degrees north, in the latitude
Mm-hmm.
realm there.
Mm-hmm.
Again, we see the dotted line in the middle is the mean temperature from 1982 to 2011. So basically a 30-year time period. The upper dashed line is the two standard deviations level, and the lower dashed line is two standard deviations below the mean. Orange, once again, is 2022, and the black is 2023.
Yeah.
And this is extremely alarming because this is sea surface. This is not air temperature. This is water temperature. With a much higher heat capacity means it has to absorb a lot more energy to be a lot warmer. And when you look at this, this is approaching 4 standard deviations above the mean.
Not good.
And
Not
no,
good.
it's not. In,
No.
in in general statistics, you know, plus or minus 3 standard deviation around the mean accounts for 99.97% of the data. So to say this is anomalous is an understatement. This is this is uncharted waters, pardon the pun. But this is really uncharted waters. And look at the difference just between 2022 and 2023 in the temperature, especially when we start getting into around the beginning of April or so. That
Wow.
is that's just huge. A huge
Huge.
difference. The
Huge.
oceans are getting really, really warm.
Mm.
Now, there are, some explanations. Leon Simons argues, and
Mhm.
he makes a good point that
Wait a
with the
minute.
reduction,
Who is Leon Simons? Remember, because we're in a group with Leon, doesn't mean everybody knows who Leon is.
Leon does a lot of aerosol work. He's worked with James Hansen.
Okay. Leon is in a group with us. We have a private group on Twitter, and I am basically just the I don't know what I am. They're the scientists. But Leon, he I've invited him to be on as our guest. Okay. Go ahead, Jim.
But he makes the argument that with the reduction of aerosol from freighter ships, for example, that allows more heat to reach the ocean surface. Um, it is a contributing factor, but as I will argue later on, it's the already stored heat content in the ocean that is also a major contributor. Is more than one factor, of course.
Wow. Wow.
The next slide is mind blowing. And this is from the North Atlantic. Now, you see a lot of squiggly stuff all over the place. That's individual years. The black horizontal line is the average. So this is showing a deviation from the average. And look at 2023. That's the orangey line at the top.
Mm.
Look at the recent trend. It looks like it's zooming upwards.
Oh my gosh. That doesn't
It's
it
it's
looks
crazy.
exponential to me. Yeah. Oh,
Yeah,
Elliot's here. He says that's my slide. It went global. Hi, Elliot.
yeah.
Welcome. Welcome. And we heard you were quoted in the New York Times too. Elliot, my gosh, you're really showing how bad things are.
Now,
Wow.
the thing is that would I expect this to continue increasing as rapidly as this is currently? Probably not, because you do have seasonality in the ocean. So at some point it will flatten out and start decreasing. But the point is, look how much hotter it is than historical records have. This is unprecedented. This is extremely alarming.
Hmm. We seem to have
Extremely
lost a
alarming.
Yeah, I would say so. It's extremely alarming. Wow. Wowie wow.
And, and what's interesting is, we'll talk more about this a little later on. Yes, the Pacific has absorbed a lot of heat, and there's a lot of stored heat in the Pacific, but the Pacific is, well, kind of big. It's a big, huge ocean. But when you look at it on a per cubic meter aspect, the North Atlantic and the Southern Ocean have actually more heat content in it in a per cubic meter consideration.
Mhm.
So it's this is just it's out of control, folks. It's just, you know as I'll argue later, we have gone past the tipping point, and we're now seeing the ramifications of everything.
What does that mean for everyday life?
Live each day to the fullest as if it were your last. You know,
Mm.
it's, I mean, it's the consequences of the exponentiation that we're seeing across whatever parameters under consideration are such that civilization, uh, very shortly, probably within 1 to 2, 3, 4 decades, will be untenable.
Oh my gosh. Well, Poppy had said, "Is any of this a surprise?" And it's kind of not. Hey, you know what?
Well,
They
it's
took.
not. It's not a surprise to those of us who've been paying attention.
Hmm, no,
But a lot of people haven't been paying attention.
Elliot has. We know that.
Well, as I said,
Yeah,
to those
a
who've
lot
been
of
paying
people are.
attention, the great majority of people on this planet have not been paying attention.
No, no.
You
Okay,
know, it's you can't argue with physics.
true,
You just can't.
true. You know what? They took us off Twitter. I don't know why. The live stream is not on Twitter. It got stopped. Huh, that's pretty wild.
That's
Broadcast is now
Elon.
available.
That's Elon Fusk
I
for
don't
you.
understand it. I was looking, but oh well. What can you do? We usually are on Twitter. I don't know what's going on. It's weird. Things get weird, but we are on Twitch with 0 viewers. That's great. All right, Jim. Keep on going.
Well, we're on Twitter just in the imaginary number realms.
Yeah,
That's all.
right. I hear you.
Take, take the square root of -1. Anyway,
Somebody doesn't
okay.
like us.
Uh, yeah, Elon Fusk.
All right.
Okay. Global sea ice. This is just an overall look at global sea ice.
Zach Labes.
Zach, our good buddy Zach Labe here.
Yep.
He creates these excellent uh, figures and charts and so forth. And what you at the very top is, going back like 30, 40 years. And as you can see, and this is showing the extent. So that would be in square kilometers
Mm-hmm.
of the ice. So how much surface area is covered with sea ice. And we can see the overall trend over the last 4 decades of decreasing extent. And 2023 is indicated in red, and it's one of the
Mm.
lowest years that we have on record. Some spots it's the lowest, other spots it's like maybe the second or third lowest, but the overall trend for the last 4 decades is decreasing sea ice.
Mm.
And it's hard to know exactly how this will play out the rest of the year. I expect it to sit about in one of the lowest sea ice extents that we have data for. So again, the further trend of increasing sea surface temperature, increasing loss of sea ice, increasing air temperature, it's unmistakable what's happening.
Unmistakable.
And then the next one is a telling one because this is looking at global sea ice volume. So now we're getting this is like in cubic kilometers,
Yeah.
and so this takes into account multi-year sea ice,
Mm-hmm.
old
The
sea
volume.
ice, ice 6, 7 years or older or so,
Mm-hmm.
and once again, the overall trend from 3, 4 decades is that of decreasing sea ice volume. And the 2023 is indicated in yellow, and it's down towards the bottom.
Yeah. We see.
You know,
We
it's
see.
it's just a continuation of the overall trend. Now, what's really particularly worrisome about losing the multi-year ice is that with the current conditions, sea ice is rarely going to survive more than 2 or 3 years right now because the heat will eventually erode it.
You're saying
It
two or
used to
three
be
years. I mean, there's a lot of different. There's a lot of different discussions on 2 or 3 years, 2 or 3 decades, depending on what are we talking about, extent.
No, no, no,
All
no.
right, yeah, okay,
Let me clarify.
do
When I'm
that.
saying 2, 3 years, and what I'm saying is that we're not going to see sea ice in that whose age is more than 2 or 3 years of
Oh,
age.
gotcha. Thank you. See, if I was messing that up, somebody else might not have understood. So it's okay. We are not going to see older sea ice any longer.
Right, where
No.
and up in the Arctic, the last vestige, 6, 7, 8 year sea ice is in the Canadian archipelago, like, for
Mm-hmm.
example, Nares Strait, and so forth. We lose that. That's kind of the last remnants of very old sea ice. So it's the trend is that sea ice that is older than 2 or 3 years is going to be uncommon. I don't see uh, sea ice. Say that fast several times. I don't see sea ice older than 4 years persisting anytime soon, or even making it that far along.
So it's
I
got to
just don't.
refreeze every year and hope that it gets to a temperature where it will refreeze every year
We got to
in the Arctic.
basically what you need to happen is that not all the ice melts, and that some of it is allowed to accrete so that it makes it through the next winter and so on.
Mm-hmm.
But given the dynamics of the heat diffusion,
Right.
the inflow through, I'm talking about the Arctic, of course, right now,
Mm-hmm.
the
Mm-hmm.
inflow through Fram and the Bering, the ice will eventually be eroded. And now with the weakening halocline, allowing for more diffusion, vertical diffusion,
Yeah.
that will also greatly hinder the capability of sea ice surviving past 2, 3 years.
That was your latest video that I watched. That was the interesting about the halocline and learning about that. And wow, it's all eye opening, but it's all the oceans.
That was a lot of the work I did was, looking at heat budgets and the halocline in the Arctic, while I was looking at in the Chukchi, which is,
Mm-hmm.
right off Alaska.
Mm-hmm.
But that was a lot of what I did. Not exciting work, but necessary work. Taking temperatures, constructing the
Sure.
heat budgets, trying to figure out the inflows, the outflows, the inputs, the outputs, and so on. Necessary work to get a handle on the physical processes, really.
Mm. There's a lot to learn
And
here.
now, yeah, there's a lot we don't know, that's for sure. Absolutely.
Oh, Jim, I
And the
have a
next,
question before you go on. So, when you did that video, and the data was from prior to the war in Ukraine. So, how are we going to get data anymore going forward from the areas that Russia controls? Are Russian scientists working with anybody in the West at all?
no.
So we're out of luck for a lot of information, a lot of data that we
Yeah,
would have had. What a shame.
yeah,
Oh
yeah.
my
I
God.
mean, you take Igor and Natalia. I mean, they went back to Russia before the war started, because of they had better appointments there. They're only on, like, on a part-time
Oh
basis
shit.
uh, with the UAF, so they
Yep.
went back. And because Igor was kind of like a head scientist there, doing all the methane work in the Laptev and East Siberian
Mm-hmm.
seas, as well as Natalia. And then this then Putler does his stupidity,
Yeah.
and basically he shut down the email. So you know Russian scientists can't email colleagues. They can't email colleagues. They can't receive email. I mean, they've been totally cut off. And so,
So
yes,
that's
we're
it.
we're, we're losing we're losing that we're losing that data.
Even though the data is to be expected, based on everything we have, and it's going to add just more. We are so fucked. I mean, basically. But it's good to
You-
have that. I mean, this is excellent important research. So
It
Rollinson
is.
said satellite data is what we get. It's just satellite data that we'll get. We're not going to be able to have anything from hands on the ground. No,
Well, hang on. Hang on. Okay, satellite data is important, but it's not the only thing. We have a plethora of Argo buoys. We have other devices that are moored at various depths throughout the ocean. We can get data from a lot of the ocean. Satellite data is great for a quick snapshot of what's happening on the surface. You
okay.
want to see where a phytoplankton bloom is, get a sea surface temperature. Yeah, satellite data is great for that. But you need other instrumentation to get to, because the ocean is kind of a 3D thing. You need other instrumentations to go further down. Now, we're losing access to the data that Russian scientists are gathering. We still have, even though they're, you know, I don't want to get political here, but even though the Chinese government is
Don't. Let's not.
not to be, but there is still Chinese scientists
hmm
that are doing work. And if you
Okay.
look in the in the last year or so, a lot of the publications in JGU are by Chinese researchers
Oh, good.
up in the Arctic.
I worked
So
with Chinese
this,
researchers. They were excellent people, excellent researchers in my years in research.
well, I worked at the International Arctic. Re- you know, you know, so yeah, I worked with scientists from all over.
Good.
Um, so we still will have the data courtesy of the Chinese researchers and what they find.
Okay.
All is not lost, but it still is detrimental not seeing the Russian input.
Yeah, I would think. I would think. We were so close. Next.
And next is the Antarctic sea ice.
No, what a mess there too.
I think that says it. And by the way, to explain what this figure shows, you see that dark blue line in the middle of things?
hmm
That's the average. Okay. And this is showing the extent, again, in square kilometers. That is the average. The shading, the lighter blue, is the plus or minus two standard deviations
hmm
from the mean.
Yep.
And the red is 2023. And as you can see, it's
It's close.
outside the plus or minus, it's outside the minus two standard deviation. So
Wow.
we're losing the Antarctic sea ice. We're
Wow.
losing Arctic ice. We're losing the Antarctic sea ice.
Wow. It is quite something.
And
Quite
the
something.
blue hashing at the bottom is basically saying, "Hey, no ice."
Yeah, you see it, and then you can see how close we are. Wow. Wow, 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 wow.
So this is just a quick representation of the latest data. Looking at global temperature at the 2 meter level, which is standard methodology. We've looked at the sea surface temperature. We looked at the North Atlantic temperature. Excuse me.
Yeah.
And then we've looked at some ice. You know, Arctic ice, Antarctic ice, extent, volume, and so forth. And I'm now going to make the argument that the reason we're seeing this is due to the ocean heat content.
Right.
So that should bring us to our first,
Yep. We're going to
uh,
get there and pull this one up. All
the
right.
climate.gov page there. If
Mm-hmm.
Yep, and I've got a pulled up on a separate tab here so I can
Okay.
like see the print here. So
All right.
anyway, so now let's look at the very first figure that we see on the top there. This
Mm-hmm.
is a figure that I'm sure many of you are familiar with. I've certainly have included something akin to this in my videos and presentation, but this is showing the ocean heat compared to the average.
Mm.
And this starts in the like 1950 or so, takes us up to pretty much 2022, and this is showing the heat content anomaly in 10 to the 22
All
joules.
right, where should
And
I be on this one?
the top, it says ocean heat compared to the
Yeah,
average when you're
because
at
it
the top.
said
Yeah.
2020. That's why I was a little confused.
Well, the graph extent on the
All right.
horizontal extends a little past it,
Okay.
so it takes us up to 2022.
Okay.
So as seeing the highlights here, average over the full depth of the ocean, the 1993 to 2021 heat gain rates are approximately 0.64 to zero point 0.8 watts per square meter. Now, that may not sound like a lot, but the planet is an ocean planet. It has a huge, high number of square kilometers. That is a high amount of heat that's been absorbed. All you have to do is take that amount and integrate it over the entire surface area to get a calculation that results in a chart like this.
Mm,
And as we can see, the overall
look at
trend
that.
is unmistakably
Unmistakably.
increasing.
Unmistakably. It's right
Increasing
here.
increasing ocean heat content is contributing to sea level rise, ocean heat waves, coral bleaching, melting of ocean terminating glaciers, and ice sheets around Greenland and Antarctica. I would also add, melting sea ice earlier, hindering sea ice formation later in the year. And I mean, there are other things going on that when you have increasing ocean heat, content, that means oxygen levels are decreasing, and that can lead to anoxic conditions with high levels of organism mortality. Because, especially an organism that requires high oxygen content, like
Mm-hmm.
a bluefin tuna, uh, you know, uh, if the oxygen levels go too low, they will asphyxiate. They will not be able to, because they have their endotherms, so they would not be able to carry on their metabolism. So, um, this, in addition to the physics, the problems presented by the physics of it, they're the
Mm-hmm.
problems presented, physiological challenges to the organisms.
Mm, mm.
Now, the next uh, point is really
Do you want me
incredible.
to go down or are we going
No,
to
no,
the
no,
next?
I'm reading the bullet points to the left of this figure here. The heat already stored in the ocean
Oh,
will eventually be released.
yeah. Already stored.
That's what's happening. That's why the air temperatures are increasing much more so. That's why sea ice is being lost. That's why Antarctica, the ice sheets are being lost. Because
S-
if the heat cannot be sequestered to depth, which is that is slowing down because
Yeah.
thermal hailing flow is slowing down due to stratification and so on. That heat is going to go somewhere. It's going to move laterally, horizontally. It's going to diffuse to the atmosphere. Okay?
It's like,
And
oh,
this heat that should be released will commit Earth to additional surface warming in the future.
oh, lovely.
And
Oh,
this is why I argue, when you compare to the aerosol masking effect being reduced, argue that the heat content in the ocean trumps that. That is going
mm,
to have a greater effect. Yes, reducing aerosol masking effect will contribute to warming. That is without a doubt.
right.
What's in the oceans will eclipse that.
What does it do to the wildlife in the oceans and what's happening now?
Oh, it's going to create oxygen. It's a lot of organisms, going to suffer from lower oxygen levels. So what happens there? Oceans get too warm for what they prefer, so they're going to move. They're going to move deeper. They're going to move poleward to try and find suitable temperatures. But then again, if they do so, will they find food? They may not find food. Or if they stay in the warmer areas, then more of
Mm-hmm.
their metabolism
Mm,
they're going to lose more of the metabolism, and they're not going to be able to devote energy to making gametes, so the reproduction falls off, or they just not enough oxygen, and organisms will die off in mass. So It's going to present major physiological challenges to the organisms, and it ain't good.
Is it like a wet bulb event? A wet bulb event in the sea? God.
That could be that could be an analogy.
I mean, it's the analogy I could think of, and the other one it was, well, with CO2 and how everything we burn, it doesn't leave. I mean, we're 20 years behind, right? So even if we stop burning, we still got 20 years of CO2. What is that doing to the oceans? You're demonstrating that right now. Right
Yeah,
now.
uh, absolutely,
Because you said
absolutely.
the heat is catching up. I mean, it's there. It's been there.
Think of the oceans right now as a huge battery, a huge capacitor. And we know what capacitors like to discharge their energy,
Absolutely. You're right.
and it's discharging right now.
It's discharging.
So
And
if
here
we
we
if
are.
we scroll on down on this site here, we come to the uh, ocean heat trend, 1993 to 2021.
Okay.
That's basically the last of almost 30 years.
Mm-hmm.
And the scale is the change in ocean heat content, and it shows it in watts per square meter, and up to 6 watts per square meter is mind blowing. And we see what? You look at the Indian Ocean, you look at the equatorial Pacific, you look at the Southern Ocean, the Southern Pacific, you look at the mid North Atlantic Ocean, the Southern Atlantic
Wow.
Ocean, and there's just a chunk load of heat that the oceans are absorbing. And also look at the North Pacific, basically level with the Pacific Northwest states and British Columbia, all the way heading all the way over to Japan. This is a lot of heat that the oceans have been absorbing.
Mm.
A lot of heat.
It's just not gonna stop. No, it won't
You
stop. So we go down to how heat moves. Mm.
And just so before we even do that, just look at the
Mm-hmm.
little caption. The
Okay.
change in heat content in the upper 2,300 feet or 700 meters
Mm-hmm.
of the ocean. Okay. A lot of the heat's being stored there because of the stratification and the slowdown of sequestration.
I
And,
see.
heat content rose by up to 6 watts per square meter, as we just looked at. When you think of the specific, I'm going to keep driving home this point. When you keep thinking about the specific heat content of water and how much energy it takes to increase, you know, temperature of water, that is a lot of energy.
That's a lot of energy. You're right. You're right. A lot of
93%
energy.
of the heat energy
Oh.
humans have released due to burning fossil fuels it has ended up in the oceans.
And people just
93%.
don't
The other
realize it.
7% is doing all the other crap we're seeing. Just wait till, even if like one third of that heat energy from the ocean makes it to the atmosphere, we're in for a wild time.
Yeah. Well, we're in a wild time, but the
Yeah.
the ocean, why are those people, Jim, that I guess you could call them what? Deniers. Yes, Darlene, I will. The deniers, they're saying that the things are getting better and the reefs are getting better. They're healing and all that. Where do they get this information from?
Um, Smoking various types of foliage, I would imagine.
My God. But that doesn't happen to us. No,
In which case,
seriously.
I would say, please share.
Yeah,
We
seriously.
can all use a hit, right?
Or two. Yeah, I swear. Oh my gosh.
I really don't I don't have an answer for that.
I just
Um,
because I see them and I see what people say, and there's so much there, and people don't know about the oceans. The average person. I mean, I try so hard to keep up with all of your videos and learn about the stratification and the heating and all, but a lot of people don't understand at all the role of the oceans in what we're looking at. Mm-mm.
and the oceans are the main climate driver. They really are.
Absolutely.
Um, You know,
Absolutely.
um, it's yeah, it's I said I don't have an answer. The only thing that comes to mind is something George Carlin once said that the,
Mm.
the average the average American is stupid and half of them are dumber.
Well,
So,
I'm starting to believe that Americans are the stupidest on the planet, although I think it has a lot to do with what is sold in the grocery stores, in the food industry. So, but that's a different show. We are on the oceans,
yeah.
and God knows what's in what we catch in the oceans. Oh my goodness.
So if we can scroll down to where it says change over time. And Sandy, I take it you'll leave the URL links in the
Oh,
comments
I'll
for
put
folks who want.
everything in the show notes. Mm-hmm.
Yeah, change over time. More than 90% of the warming that's happened on Earth over the past 50 years has occurred in the ocean, which
Mm-hmm.
goes back to what I just said about the oceans absorbing over 93% of the heat energy humans have released due to burning fossil fuels. Okay. About 63% is stored in the recent studies estimate that warming of the upper oceans accounts for about 63% of the total increase in the amount of stored heat in the climate system from 71 to 2010. And warming from 700 meters down to the ocean floor adds another 30%. So, what this graph shows is the annual ocean heat content compared to the average period looking from 1993 to 2019. Now, this is a recent, that's what, 19 and 7. So it's like what, recent 26-year, 27-year history. This
Mm-hmm.
is recent, and we can still see how much warmer things are in the last, s- basically this century.
Mm-hmm.
This
Wow.
is ocean heat content 10 to the 21st joules. So it'd be zettajoules here.
Which
I
we've
mean,
learned. Yes.
look at that. The up is just increasing. And then so the reddish lines are from the surface to, 700 meters or so. And then the bluish lines is down to about, 2,000 meters or so. And we still see the warming even down to 2,000 meters, but it's not as much because the sequestration, the vertical movement of water is slowing.
Mm.
And
Wow.
this just shows you what's going on in the oceans. And it's just mind blowing. It's just absolutely mind blowing. So yeah, it's
Makes me feel a little nauseous, sick.
I mean, what they say, a picture tells a thousand words here. You can just see it right here.
Every picture
You
tells
just
a
see it.
story, don't it? Yeah.
Yeah. I think we can pull up the next URL.
The ocean warming.
Yes,
Okay.
that one.
All right, sir. Here we go.
We'll start right at the top there. It shows you a figure. And what does the headline say? Since 1955, 345 plus or minus 2 zettajoules. That's how much total heat energy the oceans have absorbed. Now, when I did my last ocean heat update video in January 2022, it was 240, 250 zettajoules.
Mm-hmm.
So in what, 16 months, toss in another 100 zettajoules? Holy crap.
Yeah. Let me see.
And we can see it. I mean, it's doing what's the figure doing? It's doink. It's just going right up. And by the way, when you look towards 1960 and 1970, you see the blue shading
Mm-hmm.
around.
Yeah.
That basically represents the 95% margin. So basically the 95% confidence interval. And you'll see that as we get, to present day, that the 95% confidence interval is decreasing. that means that our measurements are improving, our accuracy and precisions are improving. The instrumentation to take the measurements are improving. But this is unmistakable, the trend being demonstrated here, that three, base 345 zetajoules in the ocean. Some people say up to 400, but
Hmm.
even so, 345 is an incredible amount when you consider that, 16 months ago it was 240, 250.
Yeah.
Yeah, you look at the numbers, you understand the mathematics, the function, and the trend, but it's just still mind blowing that that much in 16 months, another 100 zetajoules tossed in there, just incredible.
Back when you were an active oceanographer and you were studying, did you think that it would be like this, Jim? Did you think it would be so fast or faster than previously expected, as they always say?
I had my suspicion in the late 90s, early 00s when I started seeing the data coming in. I
Okay.
had my suspicions. I could not have foreseen it would be this bad, but I had my suspicions.
You had
But
your suspicions.
suspicions is one thing, data to verify is another thing. And, the data wasn't as convincing, 20, 25 years ago as it is today.
Mm,
But I'll explain that a little more later on.
okay.
Uh, you know, but we were seeing that because I was seeing the increasing heat in the Arctic Ocean, and I understood back then um, what bad news that was.
Sure.
I just sensed it right then. So
Wow. That's heavy.
I think we can kind of return to the other figures there, and what I want to show is
Are we right?
that one
Okay,
there.
this one. Ooh, look
Yep,
at that.
that one there. Yep.
Ooh, look at that one. Oh my God.
Now this is about 16 months ago. It hasn't been updated, but I can pretty much hazard a guess that this will be much more extensive, will be
Hmm.
spreading much further across the Pacific. This is showing the heat anomalous blob in the North Pacific,
And who's this from?
showing you. This is from Chang. Was it Chang? Yeah, Leah Chang and his team.
Okay.
Um, he does a lot of this kind of work here, looking at ocean heat content. Um,
All right.
but this shows the extent of the heat absorption. You can see it, measuring down to like 400 meters or so,
Yeah, I
and the
see it.
extent basically, from North America to Asia. And nowadays, it would not surprise me if this heat blob now has gone over the equator.
Do we know this?
That's I'm waiting for the latest generated update, but
Mm,
we have data. So if you have the appropriate software, you can plug in the data and recreate such a
mm-hmm.
diagram. And the data is showing this heat content, as we saw earlier, just with some of the prior slides we shared. We can
Yeah.
see that the heat content has moved into the South Pacific, across the equatorial Pacific, in the Indian Ocean. We can construct a similar diagram for the Indian Ocean, the North Atlantic, the South Atlantic, the South Pacific, Southern Ocean. We can construct similar diagrams and figures showing the extent of the heat blob in a 3D aspect. You know, you know, from longitude to longitude, latitude to
Wow.
latitude, from down to depth. We can create this sort of thing, and we can see that this is a load of heat. And this is
Yeah.
just the North Pacific.
Phew.
This is this is just the North Pacific here. So when This does, and the North Pacific does not have the sequestration capabilities that, say, the Atlantic does or Antarctica does, the two major places where deep water forms. So this is going to linger, and that heat is going to move laterally. So some
Mhm.
of it goes into the Arctic Ocean through the Bering,
Yeah.
and some makes its way southward to Antarctica, and some of the heat will diffuse to the atmosphere. And look at those atmospheric rivers that we just had earlier this year. Places like
Yeah.
California just getting hammered. I submit to you that it was this ocean heat diffusing through the atmosphere, bringing lots of moisture.
Is it a theory or is this something that is actually out there that you can defend?
This is based on data.
It is the data, and it is the data. So those atmospheric rivers and all of that information has been collected, and we are definitely. Are we in for more?
Most likely.
Yeah.
Of course, a lot depends on what's happening with the Eastern Pacific Oscillation, which is sort of like a subset of the PDO. If earlier this year the configuration favored uh, California getting slammed. So, uh, but we have been measuring that this heat from the ocean is diffusing to the atmosphere, contributing to the warming of the atmosphere, and then with the changing airflow patterns in the atmosphere, bringing heat and moisture, and then California got pissed on.
God, we're getting it
So,
from each end, so to speak.
yeah,
Metaphorically speaking. Oh my God, it's not funny.
it says
It's
this heat.
frightening.
Anyone thinks that the heat goes into the ocean has just disappeared and you forget about it,
No.
forever. Wrong, wrong. This
Oh,
will return, and it is returning right now.
and you
And
you show us that in all of your videos.
I try.
Yes, you do. You take the latest research. Jim takes the latest research and he breaks it down and explains it to people like me who have no clue or didn't until I met Jim, America's science teacher here, and he does. And you really should check his channel out if you have not. I mean, a lot of you are fans, but I'm just going to give him a plug because I didn't know anything, and I still really don't. But I continue to watch the videos, sometimes once or twice. And he has a Patreon too, so there. Okay, there's your plug. We all
Thank you,
got to
thank you.
eat, guys. We all got to eat, right? Yeah.
The next uh, slide, sh- yeah, that one shows how all the oceans are connected. And when you look at this here, okay, the purple is supposed to be represent deep water formation. So we see one, a couple places in the North Atlantic. We see one off the coast of Antarctica. The blue is the deep water that flows, and the
Yes.
red is the surface water. But now, keep in mind what I just showed you in the previous slide with that big ocean blob,
Yep.
heat blob there.
That
And
blob.
now take a look at what's going on in the Pacific. You see that little, movement through the Pacific Ocean? You
Yes.
see, that was nice food. Well, guess what? That's taken the heat that's found in the Pacific, and you can see one also in the Indian Ocean. That's taken the heat from those two locations, and what's it doing? Oh, it's bringing it right to Antarctica,
Mm.
and that
Jeez.
is why. And I just did a video on that,
Yeah.
explaining how ocean heat is melting Antarctica's ice. This is why we have this flow bringing all that heat, transporting it right to Antarctica, and it is melting the ice. It's melting the sea ice. It's helping any cantilevered land ice that protrudes over the ocean. It's melting that, so it's breaking away and all that kind of stuff there. It's helping to melt the Antarctica ice, which is then causing sea rise. and so on and so forth. And
Mm.
what also, and I mentioned in this video, I'm going to mention it again. Look at the circular flow, deep water and surface currents around Antarctica, and look how it connects all the oceans.
Yeah, look at
I
that.
submit to you that the Southern Ocean is the hub for the world oceanic system.
The Southern Ocean. Oh, that's
Think of it as
interesting.
the Grand Central.
The Grand Central Ocean. Wow.
You have the trains coming in and going out. That's the water masses moving in and moving out. And it, and it and it circulates that not just from the surface but down to depth. All the oceans are connected. And Antarctica is the big hub that everything spins off of and spins
And
into.
how we used to say, what happens in the Arctic doesn't stay in the Arctic is now what happens in the Antarctic doesn't stay in the Antarctic either.
Nope.
Nope. Nope. All right.
Exactly right. Exactly right.
And the
And
repercussions are felt or are felt all over the world.
oh, and it's going to get worse. Let's just put it that way. It's going to get worse.
Thanks, Jim.
And then the last slide, I know people have seen this before, but I'm going to mention this again.
This is from where? This is
This is my
IAP.
presentation,
Yeah. Oh, okay. I see it. Hmm.
but what this is showing is this is similar to the graphic we looked at earlier, but we can see, and you see that big, my clumsily drawn red arrow in there,
Yes.
but I have made the assertion, and I still make the argument, that that is when the planet went past the tipping point. Once the oceans would no longer sequester heat to depth, it
Yeah.
started accumulating in the surface, and it's leading to warmer air temperatures, warmer sea surface temperatures, increased sea ice melt, increased land ice loss, and then of course rising sea levels, etc. It's at this point in the mid 90s is when the big transition happened.
Seems
That's when the
quite
planet
obvious. Seems quite
in
obvious, and no one was talking about it.
and was people still don't want to talk about tipping points, whatever. But in my view, because of the importance of the ocean's role in the climate, this is when the planet overall went past the tipping point, and
Okay.
it's not going to reverse. Not for tens of thousands, hundreds of thousands of years.
Okay. I appreciate it.
So that
We
that's all I have. But
That's quite a bit, Jim.
but the argument I'm making is that what we are seeing now is due to the ocean heat being returned to us.
Yeah, it's quite a bit. So we're going to do question and answer. And there's somebody in our chat, Darlene. She talks about Fukushima, which we all know is a horrible thing. But I don't know what she was. And Darlene, I really don't know. I'm going to talk right to you. I don't know what you're talking about lies, because there's no lies here in the data. Okay. So let me find the questions that I did have. Poppy. So when are we boiling? Poppy's always good for a chuckle. Okay. Thank you, Poppy, darling. When are we boiling? And Gary had said that today the LA Times quoted Dr. Elliot Jacobson with the chart he made showing this change. He had to modify the chart to show this anomalous ocean increase, temperature increase. That's pretty scary. I'm glad he showed up to
But
take the
going back to
credit.
Poppy's, you know, what appears to be a tongue in cheek when we're boiling, the increasing water temperatures in the ocean is presenting major physiological problems for organisms there. For
Of course it
those that
is.
have gills and require their oxygen from the water, dissolved oxygen. So it is presenting problems to the organisms. And, one of the major uh, conditions that lead to mass extinction events in the ocean is decreasing oxygen level. Well, gas solubility is tied inversely with water temperature. Increased water temperature, gas solubility drops. So we're increasing the water temperature. What do you think gas solubility is going to do? It's going to drop. That includes oxygen.
What does it mean when Rollins Switch says it's the water vapor increase? Can we talk about that a little bit?
In reference to,
The heating? I'm not exactly
I mean,
100% sure, but
well,
maybe he can.
if he's talking about air temperature, warmer air can hold a higher moisture content. Is is that what he's talking about? And if which is correct,
Yeah.
basically, what was stat I saw? For every degree centigrade increase, it's water con uh, humidity or water vapor increases by 7%, which means you have more moisture in the atmosphere. Yeah, that's right. Every 1 degree centigrade increase, atmospheric moisture increases by approximately 7%, which means more moisture means more precipitation.
Yes.
So
Okay.
I'm supposing that was the point of what he was getting at.
Okay. All right. Let's see. Um, how about this one? Are oxygen levels tested in the ocean water? Feels like it's a dead sea, especially in the Gulf. So,
Which Gulf?
well, I'd say she's probably talking about the Gulf of the southern, about the Gulf of Mexico.
Okay. To answer the question is yes, we do measure oxygen content in the oceans. This is why we know that there are anoxic zones in the ocean.
Hmm.
Why we are measuring oxygen minimum zones, and the oxygen minimum zones, the extent and the volume in certain places are increasing. So we are gathering the data for that.
Okay. All right. Let's see. Um, Next question. Void is asking, why does IPCC ARC 6 dismiss the ESAS methane clathrate gun being triggered?
Because the IPCC is a political body.
Basically.
You know, they will
Let's blow them up. We didn't do a flush yet either. Sorry,
they
everybody.
they are dismissive of ocean heat content. They are dismissive of methane. They insist on doing linear assumptions with the modeling to the point that the models are a joke. They make assumptions that cannot be. They're assuming things in the future that cannot be verified or justified. So their results are just silly, and I'm being
Okay.
kind. Um, you know, we've all discussed, the RCPs and that kind of stuff. There, more and more models are finding that the 8.5, which is in the IPCC, is the worst case scenario,
Yeah.
is the one that comes closest to what's actually happening, and it still is inadequate. I go back to the PIK group out of Potsdam, Germany. They have their own modeling system called Climber that they've been using for 4+ decades, and which is updated every year.
Uh-huh.
And their models have been the most accurate. Also, what they do that the IPCC does not do is that they include in their analyses the interactions among the tipping elements.
Mhm.
No, it's not. Don't just look at ocean temperature. Don't
Right.
just look at CO2 level, but what happened with the interactions between the temperatures here and the removal of trees in the Amazon and so on. I did a 2-part video series looking at that.
Okay.
Um, so that, in my view, they're probably the world's premier climate research institution group.
All right. All right, Billy Joe Smo. But we still have sea ice in the Arctic, correct?
Yeah.
He's going back to when, I mean, there's ice. Obviously, you see it. We know there's ice. It's not like it's a completely melted ocean. It's the extent of the ice. It's the volume of the ice. It's not thick, big ice. People are not driving their trucks on everything at all times of the year. Things like that, right, Jim? Yeah.
Yeah, in essence, I mean, the extent is decreasing, but also, it's now melting earlier in the year. It's freezing up later in the year. It
Oh yeah.
used to be that for the areas that became ice free in the Arctic Ocean, the
Mm-hmm.
period lasted about, 5, maybe 5.5 months. It's now 7.5 months. That's
Mm.
more than half the year.
Wow.
So eventually there will be, everyone talks about the blue ocean event.
Mm-hmm.
Um, Depending on what definition you want to use, if you want to use the definition of no ice absolutely anywhere, well, then we're probably headed in that direction. If you want to use the definition of a blue ocean event, basically being sea ice total extent is less than 1 million square kilometers, well, we've already had that.
Mm,
That was in 2012
mm, mm.
and came close in 2016. So,
All right.
everyone's focusing on the blue ocean event, but we should be focusing on the diminishing extent, the diminishing volume, the
Yeah.
diminishing uh, thickness, the earlier melting, the later freezing up. That's what we should be
Well,
focusing
isn't
on.
that cumulatively kind of what Paul talks about? Or is it I mean, it's not an event that just, okay, boom, tomorrow we have Blue Ocean event. No, it's a continuum of all of the things you just mentioned, actually. That's what I
It,
thought.
it, it's the culmination for
Yeah.
sure.
Yeah. All right, let's see. Let's see. We've got that Sam Carena. As sea ice disappears, less light will be reflected back into space, and much of incoming heat can no longer be consumed in the process of melting. So, this will accelerate Arctic heating.
Yeah,
I
spot on.
am
You
Sam
you, you
Carena.
remove the albedo, that will add to the warming of the surface layers. Absolutely, and
Yeah.
which is a major reason why the Arctic is warming 4, now 5 times faster than the rest of the planet.
Pretty heavy. Okay, well, hey, Global. 1001 Doomer Jokes is the title of his new book. Thank you for sharing that. All right. We do have to keep our humor. Without humor, where are we? We might as well be dead. Jackie, I wonder how much of the data Jim collected will be used in furtherance of resource extraction. That's been my experience in the environmental sciences. Oh boy. Ooh, Jackie. Ooh, Jackie.
Well, the data is public record, so it's there if anyone wants to actually use it.
Well, they want to do. Don't isn't the next biggest thing extracting from the bottom of the ocean, deep sea extraction? I mean, I was reading about it today, and it just seems hideous.
Oh, I think I misunderstood. I thought you were talking about just extracting the data. Oh, you're talking about extracting the
Well, I
energy?
mean, they're going to use it
I'm not.
to use the data and then use it
Oh,
for these reasons. Mm,
I really,
yeah,
the data is public record. So,
right.
I mean, a lot of researchers will go into data and incorporate into studies and what have you. So, that's the whole point of science, is that we share. We don't have copyrights and trademarks on things usually.
Yes,
It shouldn't
yes.
be, so
No,
so
there
we
shouldn't
share the
be.
data because the point is to share the knowledge and increase our knowledge and understanding,
Hmm.
at least in a Thomas More utopian world.
All right, couple more. We've got quite a bunch of little things here. All righty. What are the Antarctic land ice totals?
I don't have those numbers off the top of my head, but I'm sure that it can be easily be found. Um,
We can ask
what
on
I can
Twitter. Yeah.
what I do, we can do a backwards calculation, and that there's a sufficient amount of ice that were to all melt right now, that
Right
ocean
now.
levels would increase by some what did I see the figure, like 270 meters or something like that.
Mm.
So there's a chunk load there waiting. So you can then figure out, okay, what that volume there, and then back calculate it to how much ice is there.
Jim, we've got to think of what are we going to give a flush to? I mean, there's just so much of this, and we don't want to flush Arctic ice, right? No. What do you want to flush out of this conversation? What do you want to say? I want you to go. Give me an idea of the flush.
I've got a mosquito. Hang on, there we go. Did I get it? It's a
Hey, we
mosquito
could
buzzing my
flush.
face here.
Let's flush the mosquito.
We can flush the IPCC.
Hey, the IPCC is flushed away.
But but the flushing went upwards. It didn't go down.
Oh, we saw aerosols going up. Aerosols polluting the
That, oh,
air.
that's what it was.
Yeah, it was
Okay, that's what it was.
flush
Yeah.
aerosols. Yeah. I have to then redo my video to make it go down. My God.
Just turn it upside down.
Okay, T-Bone's with us if you're
So
still
is that another use of the aerosol masking effect?
the toilet's flushing. Oh my God. All right, David, how much additional warming will the ocean release into the atmosphere? Timelines? Sounds like
Oof.
another video for you, Jim.
Yeah.
It does.
It depends on the fusion rates. Um, One can make a conservative estimate that if say just one third of that ocean heat content diffuses to the atmosphere, that could that would be sufficient to raise global air temperature another 3 to 4 degrees C. Over what time period depends on the diffusion rate. But that's 3 to 4 C in addition to the 1.5, almost 2 that we're at now. I know
Mm.
everyone says 1.2. IPC, not the IP, the PIK group folks saying we're at 1.5, 1.6 already.
Scary shit.
And they found, because of the interactions among the tipping elements, an increase of 1.3 C is enough to create all sorts of havoc in the weather systems. And guess what we've been seeing for a year or so?
All kinds of havoc in the weather systems. Yes, bingo, bingo, bingo.
And everyone talks about, I caught some flack on Twitter saying, I was being stupid, saying that the modeling indicates a projected increase of 7 to 11 C by 2100, and it's really 3 to 5, blah blah blah. And I'm like, well, it's moot because 4 C is enough to render
Yeah,
humans
it
extinct.
is moot, isn't it? It's a stupid argument. Whether how
It
hot it's
is
going to be. We're fucked whether we're at 3 or 4 or 11 or 12. Sorry, guys, but that's how it is. I know that's a stupid
exactly.
argument. It is. You're right. I am fully concurring with you. Okay, let's
It's like
go.
okay, if we all go extinct, then who's around to verify? It's
God.
like
The amoebas. Okay. Susan Fortier has a question. What's Jim's take on Japan wanting to dump all that radioactive water from Fukushima temperature wise? We can pretty much figure out what's going to happen when people eat the contaminated fish. So, does that have some kind of, because they're going to do it in the Hudson River also. They want to do it in the Hudson River, and I'm totally involved in not having that happen. So, does that kind of water make an effect? I mean, is it enough? It might be enough for radiation.
well, it depends on the amount being released. It depends if it's hot radioactive. In other words, if if it's like warm to the touch, kind of, if the radioactivity is causing it to be warmer than usual, sort of like the Earth's core. There's radioactive activity hanging on where the
Right.
Earth's core is hot. So
Oh, boy.
it depends on the on how much is being dumped, how quickly it diffuses and mixes. So what the extent will be, I don't know. I would need to see the amount involved and what the temperature regimes of that is involved. The radioactivity obviously is an issue.
Mhm.
Um, it Wally Broca, when he wrote his Traces in the Sea book, basically almost 50 years ago, still the go-to. He used radionuclide as a way to identify water masses and to trace water movements in the ocean, along with isotopes and so forth.
Mhm.
So this would be um, an unintended experiment in tracing water movement, one that
Mm.
I don't think should be carried out, but
No, of course not. All right, let's see. I have Joe. What was the okay, comment. Here's an idea. Let's throw out the politicians and put some scientists and sociologists in their place. Very all right, but we've had a few of those. Isn't there's somebody that's a
I think the
what?
problem is scientists are too smart to become politicians. Yeah,
They're
it's just,
wasted.
we want nothing to do with that.
Oh my god. All right. Let's
I
see.
certainly don't.
Um how about Billy Joe again? How about the dead zones? Are they expanding rapidly?
Well, it depends what you mean by define rapidly. Are they expanding in some areas? Yes. What constitutes expanding rapidly?
Yeah.
You know,
All right. What would you
what
what
time
what would you interpret
what
that
time
as?
scale? I don't.
Oh,
You take the data and you basically say, okay, year X it was this, the year Y it's this.
mhm.
This is the expansion. You can calculate a rate of expansion. Is it rapid? Well, compared to what?
Yeah, okay.
On what time scale? Are we talking, on a decadal scale, a millennial scale, an epic scale? I mean,
Lot of
that's
variables to
it, it,
to
it's
test.
too
Broad.
ambiguous,
Okay.
and you just all we can do is present saying this is what it was, this is what it is. Here is the rate. We can put we can quantify that, but rapidly that's very subjective, and that's not really useful.
Okay. Let's see. Carrie, will underwater volcanoes affect the sea ice levels?
Well, we had that one that went poof in the Pacific last year. Was it Hunga Tonga? Whatever. What
I
was that
don't
one? I
remember
forget the
the
name of
name.
it.
Anybody knows
But
the name, put it in the chat.
there appears to be, you know, doing some sort of contribution to, you know, particulates and temperatures and so forth. So again, it comes down to is how many volcanoes decide to start popping off, and how much do they go popping off, and how much are they how much material are they introducing and so forth. So will it do some? Probably, but unless we know the specific, it's hard to assess.
Right. That's the scientist in you. What is Jim's opinion what this will do to the environment? So, are you meaning, Gary, the ocean environment or the ocean, the problems with the ocean? What will it do to our living environments? Maybe that's how I'm going to take that one. The living environment.
Yeah, I was also wondering if he's referring to the ocean heat content. Well, the thing is, we're changing the physics of the system. We're changing it rapidly. Um, it, Ecosystems will be affected. mostly adversely. Um, like everything else, the changes
Yeah.
may come too rapidly
Mm,
to give organisms enough time to adapt.
okay.
So that will lead to uh, increased extinction rates, or at the very least, a very noticeable decrease in biodiversity or in species numbers. So there will be changes to the ecosystem, whether it's aquatic ecosystems, terrestrial ecosystems. You know, we're already seeing cases where wet areas get wetter, dry areas get drier. We're seeing precipitation bombs.
That's what he asked.
We all know
Ocean
what's
heat.
going on.
Yeah, ocean heat to
Yeah.
living environment. Like that's what I thought. Okay.
Okay. Yeah. It's going to affect, and we're already seeing that now. Floods and droughts, fires. I mean, yeah, it's going to change things. And when the ocean heat is given off to the atmosphere, it also changes the temperature and thus the pressure gradient. You
Hmm.
know, latitudinal to latitudinal.
Right.
And when you change those, when we're seeing this now, because we don't have the well-defined temperature pressure gradient, the jet streams become a meridional versus zonal, and that starts, changing the weather patterns, the distribution of heat and precipitation, and so on and so forth, which will then impact the ecosystem. So we're seeing this,
Hmm.
and it's
Yeah.
and it's going to continue.
Okay. Let's see. Does does Jim have any thoughts about how the ocean heating will affect the viability of phytoplankton over the next few years? Are there likely folks studying this?
Are there
Oh
folks
yeah.
studying this?
Oh
Oh
yeah.
yeah.
Oh yeah. I even see that.
Oh
Oh
yeah.
yeah.
Well, it's like everything else, and I've discussed this many, many times. The problem is with the ocean heat, you get stratification. Now, stratification is a double-edged sword. You need stratification so that nutrients get locked into the photic zone, which is how far sunlight energy can reach the water
Right.
column. So lock in the nutrients so the phytoplanktons can do their things. But it is also imperative that the stratification breaks down to allow the water column. And this is true whether it's in the lake or it's in the ocean, but you need to break down the stratification to have mixing.
Mhm.
And then have the mixing event, so you bring up nutrients from below into shallower layers. Then you get a stratification, locks in the nutrients, etc. If you have a situation, and we're getting almost to a point of having a nearly permanent stratification, then if there's no mixing mechanism, you're
Mhm.
not going to inject nutrients, so the nutrients get used up, and then the phytos start dying off. And if the phytos start dying off, the zooplankton die off, the fish die off, and so on. And if the phytos die off, well, they provide 55 to 80% approximately of atmospheric oxygen.
Yeah. It's a
You
frightening.
can draw the
Fright.
line from there.
It's frightening. All right, let's see. Is oxygen, Steve Angelico? Is oxygen increasing due to algal blooms? Is oxygen increasing?
Depends where you're at. Uh, Sometimes you get algal blooms that create what's called biological oxygen demands,
Hmm.
which means that, because don't forget, phytoplankton or any producers, they also require oxygen.
Right.
It's not just that they suck down CO2 and pump out O2.
Hmm.
When they're not photosynthesizing, they are respiring. They are using oxygen.
Yeah.
So you get this massive growth. You get an algal bloom. Um, they're going to need oxygen. And then they tend to use up the oxygen in the water and then deplete the oxygen for the organisms.
Mm.
The heterotrophic organisms. And this is what we call BODs, biological oxygen demand, that can lead to like fish die-offs and stuff like that. So algal blooms can use up oxygen.
makes sense. Okay, comment from Peter Wadhams emphasizes the September minimum is now down to 1/2 to 1 meter only. Wow. That was what he said the other day, I think, in a video. Uh, did you see it?
No, I did not. And what exactly were a minimum of what's being referred to there?
Oh, we'll have
I
to.
mean,
We'll.
the minimums,
I'll send you the
the
link.
minimums of many things.
Yeah, the
Yeah,
minimums of many
yeah.
things. Well, if Boyd wants to, okay. Let's see. So will El Nino rewrite the chart? And that was an earlier chart we were looking at. So will El Nino make any differences in these in this data that's current that we currently have?
Well, the indications are is El Nino is going to be a very strong one, which means a lot of uh, more so than usual heat energy pumped into the atmosphere. Um, so yeah, it will be noticeable. But I want to make this other point. When you look at what's the trend for the last 3, 4 decades,
Mhm.
when you look at La Nina versus El Nino,
Yeah.
when you look at the La Ninas of recent years, the La Ninas of recent year are still warmer. The coldest La Ninas of recent year are still warmer than the hottest El Ninos
Yeah.
of 3, 4 decades ago.
Which I have been watching and seeing. Wow. That's pretty terrifying, actually. Oh my God. Okay, I'm not going there. I'm not going there. I'm just going to go to the questions. Um, all right, let's see. Where are any more? We have a comment from Anthony that said ocean acidification is already impacting many ocean species, especially organisms like oysters and corals that make hard shells and skeletons by combining calcium and carbonate from seawater. And that's another thing I've read, and I think that's being
That's absolute.
studied.
That's
Being
that's
Mhm.
absolutely correct. I've done videos on that as well.
Yeah, you
Yes,
have.
CO2 plus water makes carbonic acid. So but the main thing that's happening is that the lysocline, which is the transition of what's called a calcite compensation depth, the lysocline is getting shallower and shallower. So generally speaking, below the lysocline, organisms are not able to draw out the calcium carbonate, be it in calcite or argonite form,
Hmm.
into and then create their shells. So, and above the lysocline, they can. So, if the lysocline is getting shallower, that means organisms are going to find it more and more difficult to make their shells.
Okay.
And so, if an organism, for example, is found at say 50 meters, and also and the lysocline is at 80 meters, okay, fine. But then if the lysocline moves to say 30 meters, they're screwed.
Wow.
And we're seeing that, by the way, in a lot of places in the ocean. We're seeing a shallowing of the lysocline, and it is impacting organisms and their abilities to precipitate calcium carbonate to make their shells, be it oysters, coral, you name them.
Yeah. And I know you've done videos on that because I watched them. Okay, let's see here. Wendy Dalis, do you foresee the July position of the ITCZ continuing to migrate northward during the remaining part of the 21st century?
That's a very good question. I haven't seen the data of that recently, so I would need to go back and check out the data on that before I can say definitively. But it has changed its statistically average position.
Uh huh.
So will it continue to move? Probably. Again, depends on the data, depends on other factors, of course. Uh,
Yes.
you are obviously referencing a video I made some time ago on that. But I would need to go back and look at that data. But it would not surprise me to see it continue to move.
All right.
And
Thank you.
keep in mind, a statistically calculated region.
Okay. And a comment, Mr. Wadhams is the Mr. Ice volume. So that's John Schmidt was saying that's it's ice volume is what.
Oh, so the minimum is September. So is
Yeah.
that if sea ice?
Volume.
Well, September is the oceanic summer, so that is when you expect to see um, uh, sea ice minimums is in September.
So there'll be more minimum on top of minimum. Okay.
Oh, so will there be record
Yeah.
low?
Yeah.
We have to wait and see.
Yes, of
But
course.
if
Of
if
course.
current if recent years are any indication,
Yeah. Yeah.
whether or not it's a brand new all-time record low minimum, it or not, or it will probably be very close to it. We'll just have to wait and see what the data tells us.
Okay. Okay. Uh, Nadia has. Is it appropriate to compare the ongoing climate environmental catastrophe to the Permian Triassic extinction? Nadia.
Well, the difference from now to the Triassic is the rate of change. The Permian Triassic took
Wait.
place over millions of years,
Okay.
that extinction.
Yeah.
It took place, so, and it was actually in two pulses. Um, this is happening so much more rapidly. The projections are that there will be extensive mass extinction, both terrestrial and oceanic, or aquatic at least.
Mm.
So, will it be uh, comparable? Probably if you look at the total number of taxa that are lost, that have gone extinct. The main difference that I see is what's going on right now. If current projections persist, the exponentiation continues, is that the rate is a hell of a lot faster.
Okay. Thank you. And Vegematic Deluxe. Hello, Veg. Do wildfires accelerate ocean acidification? All the
Hmm,
shit that falls in, all the crap that. Think about it.
that's that's interesting. I don't have an answer. Um, it'll be interesting to see if there are studies. What does soot that gets mixed into the ocean do?
Yeah.
Uh,
Horrible,
um,
actually.
you would, from a logical point of view, what comprises soot, if it comprises of, sulfates and nitrates and whatever, that can, mix with water, can create acidic situation, you know, mild acids and so on, like sulfuric and nitric, or nitrous and sulfurous. Um, that's very interesting hypothesis. I'm going to have to start
Yeah.
seeing if there's any papers looking at that.
Yeah. I think we'd all like to know because we sure know what it was doing to our lungs. Okay, let's see. Lightning Rod, hello. Do you think this year's fires are so awesome that it will cool the year out? Could there possibly be cooling in the atmosphere? Now, Jim's an oceanographer, but can you theorize a little?
Um, the, these are pretty bad fires. It could have a regional cooling. How long it will last, if it does take place, is anyone's guess. Um, don't forget when volcanoes went poof, they had to throw up a huge amount of particulate matter into the atmosphere to really have an impact on global temperature. A lot depends on the atmospheric flows,
Okay.
where the materials gets transported. You could see regional cooling, depending again where the particulates get transported to. And if the fires continue burning as they are for months on end, then that could be an issue.
Okay. Poppy says not enough smoke. She must have seen it somewhere. All right, we're an hour and a half, so I think we're going to wrap it up. Sam Carana, yes, fires bring sulfur once emitted back into the atmosphere and into the oceans. So thank you, Sam. It makes sense. It does. I mean, it's got to go somewhere, right? Besides the
Gotta
land
go
and
somewhere.
the farmlands, it goes in the ocean is sulfur. What that must do to farmland and animals and all. It's just
And of course, a lot depends on mixing rates and so on, and turbulence.
oh my gosh, there's always a lot. It's not just like so easy to say, okay, it just falls down and that's it. There's all of those different variables as you just mentioned. Absolutely. Jim, what's your take on human extinction? Thanks, Steve Angelico.
Well, the
Just
fate of all
yeah.
species is extinction.
I guess
We're
that's
no
pretty
different.
clear. Pretty clear. Yeah.
James Lovelock opined that we're currently at what 8.1 billion people on the planet now. He opined that by 2070, 2075, there'll
Hmm.
be 2 billion people, i.e., a 75% reduction in human numbers from current levels. Um, he might have been a bit optimistic.
Oh
uh,
boy.
but the fate of all species is extinction, and humans are no different. So, um, will we go extinct? Well, if evolution teaches us anything, the answer is most likely.
Scott says, ask Chat GPT. Thanks, Scott. Oh, love you guys. I love you guys so much. All right. I think we're going to have to wrap it up. And there's two things I want to poppies. It is now the fartic. Thank you, Poppy. You are definitely bringing some humor tonight. And
That's a
Kevin,
good one.
Kevin, if you are still here, another fantastic contributions to the debate from the guest Jim Massa. Well done, team. Thank you, Kevin, very much for being here. And Jim, I do want to say thank you. I don't want to go too much longer. It's an hour and a half. No, an hour and 36 minutes, but it was good because you do videos. People don't very often get to interact with you live, which they know they can do here with you as part of the team here. Continue making your wonderfully knowledgeable videos. And everyone, I want to say thank you and thank you very much. And don't forget that we will be back Friday night. Jennifer and I will be back Friday night. And thank you, Lindsay, for being here. Thank you. It wasn't easy, I know. It's a scary topic, and most of the topics that we handle are a bit scary, but they're real and they're happening. And we must deal with them. And there are many people out there to help us. There's Michael Dowd and Post Doom No Gloom. There's Carolyn Baker. There are a lot of people here with um, life rafts. So, you know, thank you, Sam. Okay, Jim, I'm going to give you the last word.
Well, it was good to be back on with you, Sandy. Thank you, Sandy. Thank you, everyone who participated. Um, it's interesting. I tend to, one can easily get caught up in the doom of this all, the doom and gloom. I I'm just fascinated by the physics of it. So that's what keeps me interested in is this, what's the physics telling us? And you can't argue with physics.
No,
We need to understand that, folks.
I should have taken it in high school, but I'm learning now. It's not too late. All right, Jim. Then we will see you on your channel, and we will see all of you guys on Friday night. Thank you all. We love you.
Thanks all.